Hello, so this is homework 3 of separations, part B. Today what we have is we're going to be deriving expression for the boil-up ratio in terms of liquid fraction of the feed and reflux ratio, and then derive an expression for determining the equilibrium liquid composition given the vapor fraction of the mole volatile component in a binary mixture for fixed relative volatility, and then we're going to write some code to demonstrate the relative volatilities of 2 and 5 at decreasing reflux ratios at certain points. And then we're going to explain the observations. So let's get started. So we have our column, which is supposed to be feed going in. So what we have is our column. This is showing our vapor coming from the bottom and then going out the top, our feed going in. So we can start by our equation for our feed balance. So we're going to have is 1 minus Q times F, which equals V minus V bar. And we can go ahead and make it so that it's V bar plus 1 minus Q times F, which equals V. Yeah. And also what we want to recall from earlier is our reflux ratio, which is R equals L over D. And what we want to recall also is our equation from the rectifying column. So just a brief overview of what we did here. The rectifying process is basically where we have our vapor going out, goes into a condenser, and then gets turned back into liquid, and then we have our distillate moving out. And we're going to use that equation, V equals L plus D. Okay, so now what we're going to do is we're going to make it L equals D times R, plug it into here where we essentially get, where we're going to use this equation right here, and we're going to do a little bit of substitution. So what we ideally get is V equals D times R plus 1 Q times F. I believe that's so L goes here. It's supposed to be a negative. Yep, and then what we're going to have is our VB, which is our bottom vapor over our boil up, our bottoms variable. So VB is equal to D times R plus 1 minus 1 minus Q times F, all that over B. And this is our boil up ratio. So now what we're going to do is we're going to define the next step. So what we're going to do is find alpha, which is y over x1, which is y2 over x2. We get 1 minus y1 over 1 minus x1. If we hash it out, we get y1 over x1 is 1 minus x1 is 1 minus y1. So now what we're going to do is we're going to try and isolate our x1, so we're going to have to expand this out a little bit. So we take our alpha, or relative volatility, and then we're going to get x1 plus, or it's minus, our alpha times x1, y1, which equals y1 times 1 minus x1, or actually we're going to go ahead and minus x1 times y1. And so if we go ahead and transfer this over and remove that x1, get alpha minus alpha times y1 plus y1, which equals y1. And so our second equation that we need, it is y1 over alpha minus alpha y1 plus y1. And actually just simplify this down to alpha times 1 minus y1 plus y1. So now this is the coding part. So I've already gotten our library set up, and I have our variables that we're going to be utilizing already set up here as well. So let's just get right into it. So we have alpha equals 3. We're going to define our x equilibrium, which I'm going to call our function, x equilibrium function, where I'm going to call x equal, and then respect to y, and we're going to return with our alpha equation that we found right here, or for our x1 equation, which is y divided by alpha times 1 minus q y plus r. And then we're going to have to define our y equilibrium, which in this case is going to be np dot line space 0, 1, 51, and then our x equilibrium, which is essentially just our x equilibrium function with respect to our yeq. And yep, that works. Go ahead and we're gonna have to find d, which is our d times zf times f divided by xd, and then we get b, which equals f minus d. Now what we're going to do is find the xb variation of this, which is zf times f minus xd times d divided by b, and then we're going to find, or plug in vb, which is what we found right here. So what we have is d plus one minus 1 minus q times f, all of that divided by b. Okay, so now we're going to find xrs, which is b divided by vb plus xd divided by r plus 1. All of that is divided by vb plus 1 divided by VB minus R divided by R plus 1. And then we're going to find YRS. In this case, this is R divided by R plus 1 multiplied by XRS plus R XD divided by R plus 1. That should. Okay, there we go, now it's fixed. And then next we're going to start with n max equals 50 xy steps, which we will have this double array looking thing, xd, xd. We're going to define our y equilibrium, which is just xd. Now we're going to start a loop for I in range of n max. Okay, so now what we're going to do is x underscore equal, should have picked some better verbiage, but instead of x equal, it's going to be x underscore equal, and then we're going to have x equal y equal, and then xy steps dot end. Y equal, and then if our x underscore equal is less than our bottom's value, then we're going to break. We're going to make y rep, which is essentially just or some of our equations above, except multiplied by equal divided by r plus 1 plus xd divided by r plus 1. It's going to have our y strip, which is essentially just our equation we see right here. dB, this is multiplied by x equal divided by VB plus XB divided by VB. We're going to have y equal, which is min of y rep and y strip. Also, one thing to point out, I got this incorrect. This was initially in brackets, but it's calling the function in respect to y equal. And then, right, we just same thing right here. And then xy steps dot underscore np dot array of Okay, so now what we're going to do is we've already finished up our calculation part. Now we have a bunch of fig dot add scatters to put in, and there's quite a lot. Dot scatter x, which equals xd, and I believe 0. Y equals xd, xd times r plus 1. There's going to be a lot of pauses within this because there's going to be a crap ton of fake dot add scatters. And load equals lines. Oops. And this is going to be pretty much copied and pasted quite a few times, and we're just going to adjust it as we need to in terms of the x and y's. Okay, so this one is going to be based off of b, so xb plus 1 divided by, I believe, VB plus 1. I think so. And then here it's going to be XB. This is just 1. And then we're going to get XRS times RZF. And then YRS in terms of our ZF. Double check that real quick. Okay, so one thing that's not 1, it's XB plus VB. So that's just a little small error, which is fine. And then XY steps. And we're going to have colon, comma, 0, 1. Kind of the same thing for y, xy steps, colon, this is for 1, and then we're going to have our xeq, yeq, then fig dot update underscore layout, and set height to about 600, width to about, I think that's, height should be 400, width should be 600, and then show legend equals false. I think that's all. Let me double check. Okay, so missing just one more code, and this is just our reference line basically. So just 0, 1, 0, 1 with lines, and then line underscore color equals blue gray. I think this is oops. Okay, so it did work, just need this division sign right there. And so what we can see is our graph. So what this represents is our operating line. So here's our stripping and our rectifying operating lines. And it shows right here where our equilibrium is met. And then these steps right here is our step function basically. showing how many steps to get to that. And one thing to note is that during this process, until it is after equilibrium, the step function does not go past our rectifying line, which is a pretty interesting observation. Okay, so now what we're going to do is we're going to go ahead and check our problem statement. So we're told that what we have to do is demonstrate our code for our volatilities to be 2 and 5. So what we're going to do is make our alpha 2. If we run all, so what happens is our it seems like our steps don't even come before our equilibrium is met. It works afterwards, and it would be practically impossible at this point for our steps to occur before that equilibrium point. And then if we make this 5, press run all, then basically what happens is now our steps are a lot larger, and it seems like there's less of them as well. And one thing to point out is that this time it does go past the rectifying operating line until pretty much this point to pass our equilibrium, but our steps become a lot larger. So if we go back to 2, run all, and our now what we're going to be looking at is decreasing reflux ratios as well, from like 1000 to 1.5 and 1. So let's look at, here's our R, there you go. We make this 1000. So our rectifying and our stripping lines basically become basically get hidden within this gray line, which is our reference, which is our operating line. This is because the larger our R gets, the closer our lines get to 1, which is that gray line, operating line that we see. So as the larger it gets, and 1000 being such a large number, it's basically just as close to 1 as possible. As you can see, that green line is pretty much almost hidden. Or not green line, but. And then what happens if we make it 2? So our operating lines are a lot higher, meaning that they're getting a little bit away from our operating line. Okay, 1.5. Yep, they're getting even further. And then if we go to 1, yep. And because of these, because of the decreasing reflux ratio, we start to lose out on how many steps we're going to have, as now, since our equilibrium is basically out of the curve, our steps do not have a starting point or a point to get to go past. And basically this reflux ratio shows a difference in or decrease in reflux ratio shows a difference in concentration. And because of this difference in concentration, we basically lose out on being able to separate it, as it becomes harder to separate it once the I guess rectifying and stripping get closer to equilibrium, and we lose out on how many steps we can have, which causes impurities within our vapor and liquid streams that come out of the tower, and basically you won't get a good amount or a good pure vapor and liquid. And so what we can do to iterate this and to reflect it is that what we can do is basically just estimate the amount of liquid within the distillate, and what we can also do is pretty much just, and by estimating our theoretical steps needed, we can also switch between the rectifying and stripping line to further, I guess, evaluate or develop the process.